Okay, we start up. We have some more students today, and as you see from the information on Blackboard, sadly the administration couldn't just give us any bigger rooms. I don't know why. Too many students at the university. Would have been a beautiful university if it hadn't been for all these students. So we are stuck with this room, sadly, and the only solution I could find then, I will take video of the lectures, not the exercises of course, and then, well, I have to edit the videos and then I put it out on YouTube during this evening. Same goes for every lecture from now on. I mean, I don't like the quality that we have on our own system, so I prefer actually to do it myself. Quality is much better, and also YouTube is much more efficient than the stupid NTNU system. So at least for now, that's it. So we have classes here, 40 seats, and anybody showing up late have to sit on the floor or look at the YouTube videos later this evening. I couldn't find any other solution, but I think it should be okay. The quality of the camera should be quite nice, so it should work. We are, well, since there are a couple of new ones here, we have started, and we have started with a crash course in OpenFOAM. And that's important. Of course, you have to have OpenFOAM up and running. So install OpenFOAM and make it run. That's task number 1 here. And that one is quite vital. When you have done that, you have the first, soft exercise. Should be out here. So play around with it. You have a lot of background material for the exercise 1. For the zip file here, I think I made a note of it here, that you may have to rename a file. That depends on which version of OpenFOAM you are running. So, and this is going to happen, say, for the rest of the semester, so be aware of that one. If you get an error, one file is missing, maybe you just have to rename it. And for renaming, yeah, you can do it with Linux command, or you can just do it by your own system, Windows, Mac, whatever. So up to you. So the first exercise here is more get to know OpenFOAM, play with OpenFOAM. A lot of you know OpenFOAM already, so this shouldn't be too hard. But for many of you, it will be the first time. So then the setup for an OpenFOAM is rather cryptic. So be prepared to spend some time on it. But I mean, this is essential. You're going to work with OpenFOAM for the rest of the semester, so get acquainted with it. So today, I'm going to start teaching about turbulence. Some of you may have had a turbulence course. Show of hands, how many have had turbulence? Well, some at least. But for many of you, turbulence is cryptic. So we will start with turbulence theory. I think there's a chair left somewhere. So of course, turbulence is just an illusion, just something that crazy pilots play around with, right? Turbulence is not easy, I tell you. So sadly, in real life, most of the flows are going to be turbulent. Hence, turbulence is a very, very important, subject in this class. We have to know turbulence. We have to learn how to deal with turbulence. So I start with turbulence theory, and then focusing more, how is turbulence done in OpenFOAM? And the next exercise is going to be about, of course, turbulence. Then the third exercise, Then I'm planning to start giving you exercises where you have to deliver a report and you will get grading on it. So then you will have 20% of the grade for such an exercise report. I'll come back to more what it is I will require for such a report. I mean, it's just an exercise, for crying out loud. You don't have to write a big book, but some points should be present. And the important point with these, say, report exercises is that you convince me that you have understood something, that you have met the learning objectives. That's the whole point. You're supposed to learn something. I don't care if your simulation is crude or not so good, but show me that you have understood the background and the theory and the setup for doing it right. If you don't have time to do it right, the way you maybe would have wanted it to be, that's okay. That's not important. So keep that one in mind. When I split you up into groups, I just use a random generator and put 3 and 3 students together. Yep.
How much time in advance do we know the groups for
how much time in advance you know the groups? Well, the sooner the better. But it's a little tricky now with the first one, because I think you have a deadline, roughly 15th of September, to decide whether you want to take this course or not. Meaning, if I create groups before that, I risk students are running away. So I have to look a little bit into that one. But I mean, as you say, the sooner the better, of course. And then you have to find each other. Your problem. Okay, any other questions before we begin? Due to the video, then I have to repeat the question because the microphone here doesn't pick up your voices. So that's why I repeat the question. Yeah?
Do you have to give you back the first exercise?
The exercises, they're actually not mandatory, but I will recommend you to do so. Put it in. If you have questions, you can put it into your, say, your answer to the exercise. And then the student assistants hopefully then will go through it and then give you comments back. So that's an option. Yeah?
Getting good grade on the report by writing a bad report but having really nice simulations? Or is it not just the other way around?
So if you have a nice simulation but a bad report, I promise you I will give you a very, very bad grade. Now the whole point is show me that you have met the learning objectives. That's the important thing. So I'll provide you with a list. Which objective are you going to focusing on this, say, exercise report? And then make sure that you convince me, yes, I have understood this. That's the important point. But the simulation itself, it can be terrible. That's quite okay. Other questions? Okay, we have an exercise later today, so I'll be available then. And the next lecture, when is that? Well, it's actually tomorrow, 10 to 12. Okay. Where are we? Not here. Come on, come on, come on. Here we are. So for Turbulence, I wanted to start here with this one. It's actually a page I found in a book about chaos. And I like this diagram. So here you have the very easy problems up here to the left. And then you have more and more unknowns, number of variables, more and more complex. And also down here, more and more degree of non-linearities. So most of this should be well known. Even viscous fluids, then we're talking laminar flow. But when you come down to the down right corner, you meet the frontier. So within this dashed line here, you are talking research. A lot of things we don't know. And trust me, there are a lot of things we don't know. And if you go all the way down here, you find turbulent fluids. So it's pretty hard. I mean, Einstein started looking into turbulence and he gave up. Come on, this is not easy. And then it says life. I think these one two should be switched. Life is fairly easy compared to turbulence. So what is turbulence? Well, we don't really have a definition, a good definition of turbulence. Maybe the best one would be, it's not laminar. Everybody knows laminar flow, so turbulence is not laminar. But we don't really have a good definition of it. It's like pornography. You can't really give a good definition of porn, but you know it when you see it. It's sort of the same with turbulence. You know it when you see it. So for a turbulent flow, it must have all these different characteristics. It is a highly diffusive flow, a lot of mixing. It's a large Reynolds number phenomena. What is large? Well, that depends. Inside a pipe flow, you should know the number 2,300. But for a flow around a building or a car or something, then you're talking about 500,000 or something. So large, yeah, it's for you to know. A lot of vorticity, a lot of small vortexes in all dimensions. It's a 3D phenomena. If you have two-dimensional structures, that's not turbulence. You can see some nice, say, vortex shedding behind, say, a cylinder or something, but they are two-dimensional. That's not turbulence. That's actually laminar, unsteady structures. So the real turbulence is always 3D. It is dissipative, it's stealing energy. So say if you have a driving force for a flow and you make it laminar, the flow can be pretty fast. But then if the Reynolds number becomes too big, it breaks over to become turbulent, and then the average velocity is going down. It costs energy to push a turbulent flow through a pipe, much more than a laminar flow. Of course, then, if you have one driving force, and you make it first laminar, and then the flow trips, becomes turbulent, the average velocity goes down, the Reynolds number goes down, and maybe it becomes laminar again. And then he can switch between laminar and turbulent. That can happen. Not easy. You can actually do that in a faucet, in a sink. If you are careful with the handle, have a nice water column coming out of the faucet, and then all of a sudden he can trip and become turbulent. And then all of a sudden, after some time, he becomes laminar again. If you are, say, careful touch there, yes, it can happen. It is, we believe, a continuum phenomena. We don't have to go down into molecular scale here. Say the tiniest little turbulent vortex motion, it's quite big when it's compared with molecular scale. So yes, we believe it is a continuum, and it is always transient. Always transient. So this is the turbulent by nature. And we believe that the Navier-Stokes equations can describe it. We can't prove it, but nobody has disproved it either, so we trust the Navier-Stokes actually covers the turbulence. Now, for this list, this is, say, the physics of turbulence. But when we are going to simulate, we are going to cheat. We can't really do all this. Running a full three-dimensional problem and transient for a simple case. Say, for instance, you do it very, very simple. Flow between two parallel plates. You put on a constant driving force, and then you will have a steady-state solution, hopefully. But with turbulence, then actually you have to do it in 3D and you have to do it transient if you want to describe everything that goes on. But the flow between two parallel plates, infinitely big, that's just a one-dimensional problem. So there, when we cheat, we are going to model away a lot of these problems so that we can do this as a one-dimensional steady-state problem. That is quite okay. Then the turbulence model have to handle all that we sort of skip. Of course we are going to do that. So either though the list here says it must be 3D, it must be transient, so when you're using models, then we cheat. And then we try to do it as simple as possible. Then maybe 1D, maybe 2D, maybe steady state. Okay, so that was turbulence for you. In the homepage, you will find a book under material. So we have it here. The book by Versteeg. So that one is actually a quite good, description of how OpenFOAM is programmed with the finite volume methods. And I think already here in chapter 3, he starts with turbulence and turbulence modeling. And this book, yeah, of course he talks too much. A lot of authors do that. But it's fairly easy to get a hold of it, and also he jumps quite rapidly into, say, practical modeling that will be quite sufficient for us. And also, he has some nice descriptions for the different models. When are they appropriate? When are they bad? So the theory here is quite good as a reference material. I won't use it at all, so I'm going to use my own version of it. But use this as a reference for turbulence. Not that many pages. Okay, so then we jump into turbulence. Let's see now. Switch off that one. Oh. Anybody got some oil? Oh. Turbulence. I can only use a part of the blackboard as the camera won't catch it. Okay, so we start turbulence models. So please interrupt me if you have any questions. That's quite nice. Always like to be interrupted, so no problem there. So now I'm going to try to give you a quick overview over all possible turbulence models. And I start with the easy one, the cheap one, and then they are becoming more and more advanced, more and more complex, more and more expensive to use, but they should cover the physics better and better. At least that's the theory. So let's start with the simplest possible, class number 1. And I think I just called that one correlations. Correlations. A very quick and dirty turbulence model would be something like this. You take your kinematic viscosity, and then you multiply it with 1,000 or 10,000 or something like that. That's actually a turbulence model. Terrible, awful, but it will stabilize your flow. Of course, this means you are increasing the Reynolds number, decreasing, because the viscosity goes under in the expression for the Reynolds number, so then the flow becomes laminar. So that's a very, very dirty model. You shouldn't even call it a model. It's terrible. Don't do it. You know Bernoulli, and then with losses. So that's one very simple, say, turbulence model for you. You have some friction factors in this Bernoulli with losses, or energy equation if you like, from basic fluid mechanics. Then typically it's a function of the Reynolds number. And it's been found then by a lot of experiments. You find some curve adaptation from a lot of experimental results, and then you create sort of an equation for the friction factor there in Bernoulli. You have several here. And this one for engineers, of course. But it works. But very simple, of course. So that's family number 1. Family number 2, integral methods. We have some here, and not so widely used, this von Karman integrated momentum equation. That's one model for you. Von Karman is based on, say, the boundary equations. And then you can do some algebra, some integral there, and find a model that actually is possible to solve almost by hand. Also another integral methods, I think it belongs here. The law of the wall. There, it's also based on some empirical correlations, some hypotheses, but still you will have a mathematical expression there for the velocity profile close to a wall. This is something we are going to use a lot, so we are going to look a little bit more into detail here. This is important. How to handle the turbulence. Typically, it's close to the walls that the turbulence is produced. And it's very, very important in turbulence modeling, how you handle the walls. So we're coming back to that one. And then we have a big family, number 3. It's called Reynolds averaged Navier-Stokes, or RANS for short. Inside this family, that is where we are going to be. There you find turbulence models that can more or less easily be included into your software. But here we have a whole bunch of these. So now we are talking subfamilies. First, we have just algebraic equations. An algebraic equation, that means no differential equation, no partial differential equation, just an algebraic expression. Fairly easy models. And they will describe then a turbulent quantity by using the already unknown, say, velocity or pressure or density or whatever. So we have several of these, and they are cheap, but some of them may be actually useful. Maybe the most famous one, Prandtl mixing length. But and Sebesi and Smith, and you have a bunch of these. So that, I mean, this is roughly where it all started. Very simple models. So it doesn't cost much, but they are not very good in describing turbulence. We have to admit that. You don't have any transport equation. You don't take a turbulent quantity and move it around and change it. So they don't describe it too well. So just a pure algebraic equation. Next family, or subfamily, we have one equation models. When I say now one equation, This is what we call a transport equation. And what's a transport equation? Let me write it up here. A transport equation, that's a partial nonlinear differential equation describing the change of any quantity. So, for instance, I want to have the rate of change using large derivatives there for total derivatives, material derivatives, whatever you call it. Should be well known from basic fluid mechanics. The change of students in our university. How does the number of students change? Well, here I will typically have a term which produces students. What is that? Your parents? You have maybe, we have some commercial about this nice university, so that's also attracting students. Stuff like that. Who produces students? And then we may have a diffusion term, a mix of students. Typically here you start at a study program, and then after a year you find this was boring, and then you switch to another program. You are still within university, so it's just a local mix, a diffusion. Okay? Then we have a negative term, the dissipation. Somebody destroys students. Bad teachers make the students leave the university for good. Or you run out of money, or you find a good job, or I don't know, get pregnant or something. So then something destroys it. This is a transport equation. And yes, it's nonlinear inside these derivatives. So a transport equation may be expensive. The Navier-Stokes is a transport equation. Actually, we have 3 of them. 1 for each velocity component, you might say. And there also you can split the right-hand side in something that produces velocity, that diffuses and dissipates velocity. So this is sort of a standard recipe for a transport equation. So now when I say down here, we have a one equation model. That means we have one such transport equation for a turbulent quantity. Which one? Well, normally, or the most popular one, would be an eddy viscosity model. You find a sort of kinematic viscosity that is not the one that you have here, the kinematic ones, but you have a function here that sort of, say, describes the turbulent in terms of an additional viscosity. So that's a simple model for you. And one famous one there that you have to know is one that's called Spallar-Almaraz, I think it was. Almaraz. That's a one equation model. That one is quite good actually when it comes to, say, external flow around airfoils. Not so stupid. Not so stupid. But you have others as well. So that's for the eddy viscosity. You have other ones that uses the turbulent kinetic energy K, just a one transport equation for that one. And we have others. But for us, Spallar-Almaraz, that is a model you should be familiar with. Then we come to the next subfamily, two equations. And that is normally where you will stop. No more advanced than that. And here you find the famous ones. You have the K and epsilon. So you have two different transport equations, one for the kinetic energy and one for the dissipation of turbulence. Another one is called K and omega, also a very famous one. K epsilon may be say, the most famous. And the reason was Spalding and these guys, when they made it, it was a sort of the first advanced model that had any degree of success. So afterwards, everybody was using that one. So there exists a lot of, say, experience with this model. Then we know where this one is good, we know where it is bad. K omega, a little bit more modern, and also a very good model you need to know, K omega SST. So maybe we can stop there. The last one, much more modern, is sort of a mix between the two first ones, trying to use where these different models are good. Typically, in general terms, K epsilon is very good in describing external flows. Flow around a car, around a house. The K omega, much better for internal flows, inside a pipe or a channel or something like that. K omega SST, try to mix this one and use where they are good. And then use some, say, a hybrid smoother between them in some region inside your flow. And for a problem, if you have no idea what to use, you will use K omega SST. That's typically a good place to start. But sometimes you have to investigate. If I switch model, does my solution change? Which solution was the best? Your problem. Not so easy. The industry, they will typically stop here. They don't do anything more advanced than this. And they will say, oh, you have used a two-equation model. Oh, fantastic. This must be in the real truth. Researchers, academic world, we don't do this at all. We go further down. More and more advanced models, of course, we do that. In this class, you will hardly have time for it, but I'm going to teach you a little bit about it anyway. We have here something that is called an algebraic stress model. Algebraic stress model. I'm coming back to what this is. For short, an ASM. And then the last sub headline here will be a full Reynolds stress model. Reynolds stress model. Reynolds stress model and RSM. Very short description. An ASM, he will use the solution from a two-equation system and then apply some algebraic equation to get some more information, more detailed information, but purely algebraic equation. So when it comes to computational costs, these two here will be roughly the same. You have the Navier-Stokes. In 3D, you have 3 transport equations, and then here you have 2 more. Here also. In addition, some algebraic equations, but that hardly costs any CPU at all. So the ASM model, more advanced than two-equation model, but cheap. The Reynolds stress model, that's a different story. Here you are talking 7 additional transport equations to the Navier-Stokes. Thank you very much. This is not for amateurs. This is heavy. And the more advanced models here, the more parameters, the more constants you have to play around with. And that can be tricky to find. The simple models here, they hardly have any parameters at all, 1, 2, 3. Down here you are talking 20 to 25 parameters that have to be given a value. And then which value? Oh, that's your job. Yeah?
What are the like different types of run types, or like runtime in, like say, compared to each other? Like what runtime are we looking at? Or let's say the one equation.
You're thinking CPU tau? I mean, which one costs CPU? Yeah. You can't really give a number on it, but you can do it like this. more and more CPU, memory, and cost. More and more expensive. I can't really do it more precisely than that. But I mean, you know, from Navier-Stokes, if you want to have a solution there, okay, then you have 2 transport equations in 2D, or 3 in 3D. And then, okay, here we are talking twice as much, at least. And also, the turbulence here, it may require, say, smaller time steps. So it can even be more costly for that reason as well. So it may be expensive, yes. And it will be more and more expensive. Other questions? That's okay. Then we continue. After family number 3, I'm going through the details here a little bit after the break. But we have a couple of more that you need to know. So we have something that is called a large eddy simulation. Large eddy simulation. For short, LAS. Before I describe what that is, I want to tell you the last one. That is number 5. A direct numerical simulation, a DNS. So first was a DNS. Remember what I told you first. We believe that the Navier-Stokes describes turbulence. And the turbulence is 3D, transient. So we only need to solve the Navier-Stokes. And with the DNS, you don't use any turbulence model. You don't cheat. You should describe everything, every tiny little vortex inside a turbulent flow. And that's not easy. I mean, go down to the river and look at all the vortices in the river. Thank you very much. Flow around a car. Oh, you have to have very, very tiny cells to describe everything that goes on. So here you are talking supercomputers. The most heavy simulations that is done on this planet is here. It's very, very expensive. And it quite rapidly blows your memory out of proportion. As a hint, the number of cells, it will go like your Reynolds number raised to the power of 9/4. Okay? That means if you have a Reynolds number of 1 million, then you can take 1 million to the power of 9/4. That's the amount of numbers you need to store in your computer. Just forget it. We don't have that big computers on this planet. Not yet. So this is limited. Describe everything. With large eddy simulation, then we would like to do a DNS, but we can't afford it. So here we cheat. Say we have maybe our small grid cells. They are, say, 10 times too big. We know we have tiny, small little motions inside the cells that we are not able to describe. So we use a very cheap little turbulence model to describe the turbulent activity inside each computational cell. And there typically we use a very cheap turbulence model like Sebastian-Smith or Prandtl-Smith mixing lengths, something like that. And then we sort of simulate the large scales, the large motions, the large eddies. And then we model the small ones. I mean, these large ones that are important. So here you may say divide this number here, the number of cells, with a factor of 1,000. So still expensive, but say, much more possible to run even on a laptop, if you keep the Reynolds number fairly low. One important thing for these two families here you can't cheat anymore. So here you have to simulate 3 dimensions. They have to be 3D, and they have to be transient. You can't avoid that if you want to have it correctly. So even though your problem is a nice and symmetrical problem, so you could do a 2D description of the geometry, and maybe you are only interested in a steady state solution, but there doesn't exist a steady state in these two families. So you have to do a full 3D, you have to do it transient, independently of your problem. So very, very expensive. So not for you guys. It will be way too heavy. You're going to blow the memory, and you're going to blow the CPU time here. Also, when you look at, say, a DNS there, say for instance, I want to simulate the flow between 2 parallel plates. I have a driving force here. Pressure 1 is then bigger than pressure 2 on the other side, so I know the flow goes from left to right. And a turbulent velocity profile, on average, well, he may look something like this. Typically quite flat, and then sharp shoulders towards the walls, where you have no slip condition, 0 velocity there. So it's actually a one-dimensional problem. So that's fair enough. But if you want to do a DNS or an LES on such a problem, you have no choice. It has to be full 3D, like that. So you need say both X, Y, and Z direction here, although the only change is actually from wall to wall here. Now this velocity profile, this is on average, meaning you do a lot of simulations and you have a lot of results. And then at a given time, you have one example for a solution of the Navier-Stokes. But that's just one example. Then you simulate further in time, and then you get a totally different solution. That's also a solution to the Navier-Stokes. So you have to have thousands of different solutions to the Navier-Stokes and then create a good average. So